Right, what we're doing now is moving on to some further techniques, the things that will be tested in the exam. Okay, and just to put it right, that doesn't mean you can kind of forget everything we've done up till now, because a lot of them things, the basic differentiation and integration techniques, will come into these further techniques as we go along, the different processes that we're going to go through. Okay, so further integration techniques. Functions that require integrating cannot always be done in using one of the standard forms. So there isn't always something that looks like your function in the table. And you've already seen that. We've gone through numerical methods of integrating, for instance. We looked at the bisection and Newton-Raphson's method of doing finding the roots. So I've included a new table just in case you've lost the one that you already had. And talking with the other group yesterday, I reckon I could do a raw and trade, charging 10p for charity for extra copies of the tables of derivatives and integrals in these classes. However, it is possible, so I've repeated the table of standard integrals, the one that we've been using. I won't be giving you any functions outside of that table, and that table will be included with the exam paper anyway. Okay. It is possible to use some further techniques to change the function into a suitable form that can be integrated using the table. So what you do is there's a range of processes you go through to turn a particular function into one that you can integrate using the standard table. We're going to consider over the next few weeks 3 different further methods of integration. One is integration by algebraic substitution, which we're going to be doing this morning. The second one, integration by partial fractions. So what we're going to do in this afternoon session is revise partial fraction techniques, and then next week we'll be able then to integrate those partial fraction functions using normal use of the table. And then the third is integration, what's called integration by parts, which we'll do next week. Okay, so that's what we're going to be looking at today and over next week. Okay, so if we take this function, determine the integral of cos brackets 3x plus 7 dx. We don't have anything in the table of derivatives that looks like that. We've got a cosine, but it hasn't got a brackets and plus anything involved with it, and therefore it wouldn't work without using extra techniques to integrate it. Okay, so it doesn't look like anything in the standard table, but we can solve it by making what's called an algebraic substitution. So I'm going to go through this one. What we do first is we say let u equal 3x plus 7. So we make a substitution for the function inside. This is kind of like a function of a function in a way, because 3x plus 7 is a function of x, and then cos is another function, so you've got like a function inside a function. But we had that with the function of function rule in differentiation as well. So this is a similar thing in a way. Okay, then what we do, I'm going to put that over to one side. And over this side, we let the u by dx equal, oh, hang on, I'm doing that wrong. If we do that, what happens when we differentiate, sorry, to get du by dx? So differentiating what we've made equal to u. What happens? What happens to constants when you differentiate them? Yeah? Well, the whole process is integrating, but a lot of these processes you're going to find involve you differentiating some parts to rearrange them. So if we differentiate 3x plus 7, what do we end up with? 3, yeah, because the constant disappears, yeah, and 3x becomes just the constant 3, yeah? So you kind of remember that. You're going to need your table of differentials as well as your table of integrals today. All right? What we can then do is rearrange this, okay, because it needs to be dx equals something. So how can I rearrange that so that it says dx equals? Dx is going to come up here, 3 is going to come underneath, isn't it? We multiply by dx, we get du is equal to 3dx, and then divide by 3, get that, yeah? So just rearrange that for dx. So we've integrated, we take that, we integrate to get that, and then we rearrange to get it in terms of dx. Okay? What we can then do is write our function out again. We're looking for the integral of cos 3x plus 7 dx. We can say that is equal to, and what we then do is write the integral again, but write cos u, yeah, and then dx is du over 3. Yep. So what we've done is taken u and put it in there, because we said u is equal to 3x plus 7. So we've replaced that with u, and we've replaced that with du by d3, du by 3. Yeah. This bit here, do you all understand that that could be written as a third times du? Exactly the same thing. And what can we do? We're going to evaluate this integral now while that bit in the brackets is equal to u. So what can we do with constants in integrals? Because remember, there's a multiplication between all these. We can take it outside. So the first thing we can do is say that's equal to a third times the integral of cos u. Now does that bit, that integral, look like something in a table of standard integrals? Yeah? So the integral of that is 1/3, and then we're looking at the cosine of ax is equal to 1 over a sine ax plus c. Yeah, that's the entry we're looking at. There is no a as 1 in this case, so that's simply 1/3 sine u plus c. All follow that? And then lastly, we rewrite u as 3x plus 7. So we've done the substitution. Now we put what we call u back in to get our final answer. Sine 3x plus 7 and the constant of integration. You all follow that process. I'll just sum that up for the video. We've got this function that isn't in the table. Find the integral of cos 3x plus 7. First thing we do is let u equal the bit inside the brackets. Then we differentiate it and rearrange so that differential is in terms of dx. We then write out that function is equal to, and use u instead of the bit inside the brackets. And we write this rearranged du over d3 for the dx on the end. Integrate that integral, so the constant of 1/3 came outside to end up with that. And then the last thing we do is replace u with what we called u in the first place. And if you was unsure whether you got that right, what's the easiest way to check? Differentiate what you ended up with, and you should end up back where you started, which would involve you using the chain rule because it's a function of a function. Yeah? Okay? Everyone happy with that example? So let's have a look at a second one. Here we've got a function, and we have done a function before where we've had a bracketed term squared, and we multiplied out the brackets to start with, and then integrated each part separately. Okay. We could do that with this function. We could multiply out the brackets 7 times and end up with a long, difficult function with an x to the 7th term and x to the 6th term and so on. We could do that, but that would be somewhat messy and prone to mistakes, in our opinion. So instead, we can apply this integration by substitution to this function. So the first thing we have to do is say let 2x minus 5 equal u. Really, we should say that the other way around, shouldn't we? Let u equal 2x minus 5. Differentiating that, du by dx is equal to 2. Yeah. Therefore, dx is equal to du over 2. Rewrite the integral. So the integral of 2x minus 5 dx is equal to the integral of u, and that's to the power 7, isn't it? U to the 7, and du over 2. Everyone following? What can we do with the half? Take it outside. Now we've got something that we've got in our table on the front page. We can integrate this by using the integral of ax to the n entry in a table. So that's a half times what happens when we integrate u to the 7. What's the process? Add 1 to the power. Divide by the new power. So I weren't lying when I said you need to remember those old techniques. We can get rid of this half now. Half times an eighth is a half of an eighth is a 16th. U to the 8 plus C. And then we just simply replace u with what we called u in the first place. So we've got a 16th (2x minus 5 power of 8 plus c). Easy so far? What's going to need to do for these techniques is remember the process. Be able to recognize that it requires a substitution, and then what the process is to substitute u in for the function inside, differentiate, arrange, integrate the function with u in it, put whatever you said was equal to u back in at the end. Yeah? That process will not be included on the exam crib sheet, as it were. Okay? Because it isn't a formula, it's a process. Okay? So let's have a look at another one. Example 3. Find the integral of 4 over 5x minus 3 dx. So what are we going to let u equal to this time, do you think? Let's try that then, shall we? Let u 5x minus 3. Du by dx equals 5. Therefore, dx is equal to du over 5. So now we rewrite 4 over 5x minus 3 dx is equal to the integral of 4 over u du over 5. What can we take outside brackets here? Or take outside the integral here? You can take 1 over 5 out from this, and this is like 4 over 1 times 1 over du, isn't it? So you can take 4/5 outside the bracket, or outside the integral. All see that? We could take that constant 4 out, leaving 1. We can take that constant of a 5th out. So we actually got 4/5 outside and 1 over u inside. Is that in the table? 1 over u. What's the integral of 1 over u? ln u plus c. And then we just simply replace the thing we called u with what we called u in the first place. 4/5 ln 5x minus 3 plus c. So that's what happens when we integrate a function that is a fraction with a function of x as the denominator. You might come across that a few times pretty soon. Okay, functions like that. Right. So we're going to look at one more example and then leave the rest of the session with examples for you to have a go at and me to help when you get stuck. But lastly, I want to point out that we can evaluate definite integrals using this technique, because after substitution, when we get to the end, we can put the limits in and evaluate the definite integral. But just go through this example. So what are we going to let equal u here? We've got, I'm going to write this out a bit bigger. We're looking for the integral between 1 and 0 of 2e to the 6x minus 1 dx. What would you let equal u here? Let u equal 6x minus 1. I'll go with that. So du by dx is equal to 6. Therefore, dx is equal to du over 6. We can write our integral again between the limits of 1 and 0. Of 2e to the 6x minus 1 dx is equal to the integral between 1 and 0. There's a danger here in the limits while you're in terms of u, the limits aren't really valid because the limits are values of x. So what we should be doing here is finding the indefinite integral first. I'm going to put that up here. Then put limits back. There is a technique where you can change the limits, the ones in terms of u, during the process, but I'm not actually teaching that. I'm staying away from that. We're going to find the indefinite integral first, and then put the limits back in once we've done that. So we take those limits out, and we can say that is the integral of 2e to the power of u times du over 6. What constant can we take outside the integral here? One over 6 and 2, so 2 over 6, which is actually equal to 1 over 3, yeah? So a third times the integral of e to the u du. Yeah, all happy with that? What is the integral of e to the u? In the table. Don't need any brackets actually. What does it say in the table? That'll be e to the x. So the integral of e to the ax is 1 over a e to the ax. What's a equal to in this particular case? 1. No, u is in place of x here in this particular case. So u is what would be x in that. So a is 1, isn't it? So it is simply a third e to the u plus c. And then we replace u with what we called u in the first place. So it's a third e to the power of 6x minus 1 plus c. What we can do now is say thus the integral between 1 and 0 of 2e to the 6x minus 1 dx, what we started with, is equal to, in brackets, and that's a third of in brackets e to the 6x minus 1. What happens to constants when you change to definite integrals? They cancel, yeah, they disappear. So that's equal to a third times e to the 6th times 1 minus 1. So that's the value when x is equal to 1 minus e to the 0 minus 1. Because 6 times 0 is nothing. So we've put our limits in. Remember, that's the term with the upper limit, take away the term with the lower limit inserted. Upper limit's 1, lower limit's 2. So that's a third times, what does this bit evaluate to? E to the 6 minus 1, so that's e to the 5, that bit. And e to the minus 1 is put that in there, e to the 5. The answer you should get with your calculators is 49.35. So we can do definite integrals, but what we do is use the process to find, so the same process to find an indefinite integral first. So we go through the same process. Here's our definite integral, but we initially go through the process of substitution, a value for u, to end up eventually with a indefinite integral. Then we put the limits in, having found that result, and evaluate to a final answer at the end. Yeah. So on the following page of your notes, there are a number of problems involving integrals that require you to go through algebraic substitution for you to have a go at, because there is no substitute for practice. The more times you go through that process, the more the better you'll get used to it in terms of being able to do that for the exam. And eventually, the partial fraction technique requires a substitution as well. So, all right. So, have a go. See how you get on.